to see you all. I've had my little bout of illness. I'm ready to get this show on the road. So what we're going to be doing is just finishing off 8.3. That's what we need for our test. There are videos up now for the other things that I didn't have time to cover. I've been told once that it's not too bad. The stuff that I wasn't here to cover, but I've made the videos for, which is basically finding centre of mass. So if you look those stuff over, you should be well prepared to do it. On the other hand, this here isn't going to be so easy. So I'm glad I'm here doing it, not you trying to watch a video and then not being able to ask questions. So essentially what we're going to do is find the total hydrostatic force working on a plate submerged under the water. So I guess if you're into the Navy or into submariners, this is the kind of thing they're interested in doing. If you take a plate, a metal plate, let's say, and we're ignoring the thickness of it, we're just taking it as a side on, and you submerge it in the water, in this case 2 feet below the water, and the plate is 10 feet by 6 feet, then there is water pressure. Hydrostatic is just another word for water pressure. There's a water pressure force pushing against that. And the force depends on the depth of the water. So the force that's pushing on that last couple of inches here is much greater than the force of water at the top. So you can see that the force acting on this plate differs as you go down deeper and deeper in depth. Does that make sense? If you're 200 feet under the water, there's more water pressure on you than if you're 2 feet under the water, right? So we're going to be essentially doing one calculation only. We're going to be finding this total hydrostatic force. And it has a couple of quibbles, a little idiosyncrasies. Here's the first one. If the question, as it is in this one, is all about feet, then the formula for getting it is the integral from A to B, 62.5 times the depth and the width. And these are placeholders. The depth we're talking about here is the depth of a typical strip, that little red guy there. And the width is the width of that strip. And then 62.5 times the depth in terms of x times the width in terms of x. And then you integrate it, of course, with respect to x. So let's talk about this magic number 62.5. That's always used when it's pounds and feet being used. 62.5 is what 1 cubic foot of water weighs. If you didn't know that, that's what it weighs. And that's why that number is there. Now, if the units are in kilograms, meters, that kind of metric units, then the total hydrostatic force F is the integral from the start depth to the finish depth. That's what A and B are representing essentially. 9,800, that's the magic number, depth, width, and dx. And that 9,800 is because 9,800, 9.8 is the gravity bit, and the 1,000 kilograms is the water bit. So when you put them together, 9,800 is the mass of a cubic kilogram of water. I should say a cubic meter of water. So 9,800 is the mass of a cubic meter of water. So let's show you how you go about these. This is the simplest shape that you can do, which is a rectangle. So there's one in the book. It's called 14. So it describes a tank. I'm going to use these numbers. So in my case, it's 2 feet, submerged 2 feet below the water. And this rectangle is 10 feet by 6 feet. And we'll kind of do this in the form of step 1, 2, 3, 4. So step 1 is decide what to call the distance x. What on earth do I mean? There is going to be a arbitrary strip, this guy here. And we have a distance called x. X is just going to be a way that we can talk about where this thing is. Now you might say, well, that's pretty obvious, and I think it would be, that wouldn't you probably call x the distance from there to there? That seems reasonable. And that is an acceptable distance. But there are going to be questions where, to make the math easier to do, you're going to call the distance from the top of the shape to that strip x. And yet again, there's going to be another situation where we're going to make x be the distance from the bottom of the shape to that strip. So there are 3 places you can call x. From the surface to the strip is very common. From the top of the shape to the strip will be called x. And from the bottom of the shape upwards, it's going to be called x. Now, you might think, why is that important? For a rectangle, it's not important at all, because all of them end up working out pretty good math, and they all end up being correct, because it's the same thing. But in some shapes, measuring x from the top to that strip is not a good idea. The math comes out really ugly. But if you choose the top of the shape to that strip as being x, the math comes out much nicer. So in this case, I'm doing from the top of the shape, which I suggest that you do whenever it's a rectangle. Make x the surface to the strip. Step 2 now. Find the values of A and B. You see these guys here? I am interested only in this rectangle. A is going to be the distance, the depth from the surface to there, and B is going to be the distance from there to there. So there's my A and there's my B. Think of them as like the depth, right? So if I make A 2 feet and I make B, well, you tell me, what number will B be?
Eight feet.
Maybe 8, right? 2 plus another 6. Now, again, that hopefully is pretty straightforward. For rectangles, it typically is. It gets much uglier when the shape changes. Right? It's less obvious what A and B are. And you need them because, right, they have to go here and here. Now, step 3 is find what the depth is of the strip using x. Well, this is going to be dead easy. Would you agree that the depth of that strip is x? Because we measured it that way. Step 4. Find the width of the strip. Would you agree in this rectangle, it doesn't matter where the strip is, isn't it going to be the same length, right? The same width each time. And the width of this strip is going to be 10. Moving on to step 5. calculate hydrostatic force. Well, we've got our formula. It's this one, since we're working with feet and pounds. And it's going to be the integral from A to B, 62.5 times x times 10 dx. So it's going to be the integral from 2 to 8. If you multiply them together, you get 625, and just pulling out the constant, 62.5 times 10, 625. And then you get 1/2 x squared, x equals 2 to 8. 625. Well, 1/2 times 8 squared, and 1/2 take away 2 squared. What's that going to be? 625, 32, take away 2. That's basically 30. So here we go. 625 times 30. And the answer I get is 18,750. And the force is in pounds. So the total force acting on that plate is well over 18,000 pounds of force. So you can imagine that submarines who go down a lot deeper than 2 feet off the surface must have a phenomenal amount of force, water pressure, fishing on them. I mean, that's 18,000, and look, it's only 2 feet under the water. It's not even a big plate. It's not as big as a submarine by any means. Any one of those steps that you're not sure about where the pieces came from? Are we okay with that one? Rectangles are typically the easiest of the shapes to do, and that was 14. Okay, the next shape we're going to do is a triangle. We're going to do a right angle triangle, so might as well pick 15 to represent that. Here is the water surface. Here is the right angle triangle. What do we know about it? It's 2 feet below the surface. We know that this fella is 6 feet by 7 feet. Okay. And everything is in feet, so we're going to be using the 62.5 guy. Now, you do a horizontal strip at some random point on the shape. Now, in this case, it's better to choose the X guy. As that distance there. Now you say, could I use the top? Yeah, you could have used the top, but will you trust me, the math gets really ugly if you do. So in most shapes, it's better to choose the top or the bottom of the shape as this X distance. So decide what you're going to call the distance X. I'm going to call it from the top of the shape to the strip. So that's step one done. So if you ever get a triangle or a circle or half a circle, it's probably a good idea to think about the top of the shape to the strip as being your x distance, or as you're going to see from the circle point of view, the bottom of the shape to the x is also allowed. So if you want to, you could call the distance from where my finger is to that 6. You could call that x. That's going to work perfectly fine as well. Now, step 2 is basically us going to find the A values and the B values. And I'm putting in step 3 at the same time while we're at it. The depth of that strip is the depth underwater. It's that distance there. Now that distance from here to here is not x. What is the distance from here to here?
2 plus x.
Okay. Now back to the A and the B. 0 to 6. When x is 0, would you agree that you're at the top of the shape? And when x is 6, do you see how you're at the bottom of the shape? So if you decide to measure this shape by using the distance x from the top to the bottom, can you see you're going to do a 0 to a 6? So you notice how the A and the B values are not 2 to 8, but 0 to 6. And the reason why they're 0 to 6 is, do you notice how the depth has added on the extra 2 already, so you don't want to double dip. Are we comfortable about how I got the A and the B and the depth? I'm counting the shape x from the top of the shape to here. That means A is from the top value, 0, to the bottom value, B is 6. The depth is from the surface to here, and that's 2 plus x. That's how we got that. Now, it gets messier for step 4. We need to find the width. I'm going to call that guy W. And we need to find out what that width is in terms of x. Okay. Now this is where it gets a little bit different from what you've typically done. I'm going to use the thing. Oh, you tell me.
Tangent. If we found the angle of the bottom angle, wouldn't we always know what W would be then?
Well, you would need to know one of these two sides, wouldn't you, as well?
Yeah, because we'd also always know the X depth side.
Mm-hmm. I'll hold that thought. I'm not saying that's a bad idea, but there is
a complicated idea. I hope there's a simpler one.
Yes, there is. So what I believe is a simpler one. We're going to use a technique called, whoops, I put the word at the top, similar triangles. It's quite a common strategy for these shapes. Now, if you've not done similar triangles at all, which I sorely doubt, but you've probably not done them often or any time lately, what we've basically got is a big triangle, the 7x6 guy, right? The whole triangle. So we got a 7x6. Now, on the bottom here, we've got a little baby triangle, right? Looks like that. And on this side, there's W, because it's this fella. And what's that distance from here to here going to be? This is 6, the whole thing. The top piece is X. What length is the bottom piece?
6 minus X.
Now, when you have two triangles which are the same shape but different sizes, they are called similar triangles. Anybody remember similar triangles? Now, one of the nice properties about similar triangles is described as corresponding sides have the same ratio. What that means is that if you take this 6 and you divide it by the 6 minus 6, and you take this 7 and you divide it by that W, these ratios are equal. Now what you've got here is a little fractional equation, which I'm now going to do cross multiply with. Okay. And that's going to get me 42 take away 7x equals 6w. Then I'm going to divide everybody by 6 to get 7 take away 7, 6x. You see, I've now found the width in terms of x. So I use similar triangles to find what the width is. Now we're on to step 5. Let's get the total hydrostatic force. It's going to be the integral from 0 to 6, 62.5. The depth times the width, dx. So it's going to be the integral from 0 to 6 of 62.5. The depth is x add 2, and the width is 7 take away 7, 6 x dx. Right, I'm going to pull that 62.5 out right away and FOIL what's left. So I'm going to get a 76x squared, 14, and lastly a negative 7/3 x. Let's see what we get now. Get negative 76x squared. Those two don't play well together. It's really 2 1/3. So what do you get? You get 4 2/3, which is 14/3. And at that point, I'm just going to ... Would you agree that is just an ugly power rule? Evaluated at, in this case, 0 and 6. And then don't forget to multiply by 62.5 when you're finished. And I'm just checking what they say it is. They say it's £5,250. I'll take their word for it. Oh yeah, I can imagine. Won't all these 60s probably play well, and thirds will play well with this? So yeah, I can imagine all the fractions disappearing. Now it's a lot different, a lot messier than a rectangle. Agreed, rectangles are pretty much what you see is what you get. You don't really need to think too much. But a triangle, not so obvious. Oh. WebAssign is calling that guy there delta. So in one of the questions, I'm just looking at the answer, they put a delta in there because they felt like it, I guess. Just when you're setting up the integral. Okay, let's look at
415. They also require we use the integral from A to B. Yeah.
Yeah. Do you know what they did in that question? What I did and they didn't. Right. They decided to make, I'm assuming they decided to make that distance there x, in which case this would be 2 to 8. Yeah.
Would that mean that most of everything we did is the same, except for the depth is x instead of x plus 2, and then in step 4,
there'd be an ugly looking version of this.
Yeah. The initial would that just make the initial fraction like 6/6 minus x minus 2?
I don't know. It's a short answer. I'd have to redo it again from scratch to make that kind of work. If I have time, I'll go back to that one and do it in their order. The thing is that since there's 3 ways to do this, can you see that if you go route 1, you're going to get different looking math. You're still going to get this as the answer, but you're going to get 3 different ways of, what's the analogy? Can you remember the buckets of water being lifted up the cliff? And I always count X from the top, but if they count X from the bottom, doesn't the math look different, but the answer looks the same? So I'm not too worried in a test which one of the 3 versions of X you want to choose, right? Because you're going to get the right answer, at least when you do this one. You're going to have problems if you randomly pick one when you're doing a circle. Guess what I did? I'll do another triangle one. That sounds like a good plan. And I'll try and do it from the orientation that they're using. But to do that, I'm going to have to look at what their answer is. Okay. So in question 16, they have a triangle that looks something like this, which is an isosceles triangle this time. And that distance there is 7. And this vertical distance here is 8. And are we still in feet? No, we're in we're in meters now. Okay. Well, we can deal with meters usually. Now, when you do metric system, the number that's here, this here is called delta. When you use this number in metric, they're going to call it rho G. G is gravity and rho is the thing, so rho is density of water. These nitpicky things that engineers make us worry about distracts me totally from the math, which is how do you get the answer. So let's see what it's going. It's going from 0 to 8. Okay, so if we do our strip here, and we decide to call this distance here X, doesn't that look like the top of the shape down? Right. And that's the one they're using. So in this story, we've got X done. So there's step 1, check. Step 2, won't A go from the top, which is 0, to the bottom, which is 8? So that's 2 done. 3, and would you agree that the depth of this strip is just X? Are we okay with 1, 2, and 3? Because in this particular question, if you make X the distance from the top of the surface to the arbitrary strip, that makes A go from 0 to 8. That makes the depth X. So all we need to do now is figure out what the width is. So I'm going to have a little bit more problem with this fella. Do you agree? Okay, so you might think I'm going to do this guy, right? And then a big guy. And that's going to be my 2 similar triangles. That's not actually how we're going to do this. And the reason why we're not going to do this is, well, I've got, well, let's take this out. I may change my mind actually. There's 7 and 8. And maybe I will change my mind. That is X and this is W. Oh, I take it all back. This one's coming out quite nice. Right. The little baby triangle is this fella. And he is unknown width, distance X. And then the big triangle is 8 and 7. So corresponding sides, X over 8 is going to be W over 7. 8W 7x. That makes W 7/8 x. I was surprised how much that came out. So we use similar triangles to figure out what the width is, how wide that strip is in terms of x. So we should be able to put it all together now. It's going to be the integral from 0 to 8. To keep WebAssign happy, I'll put row G here instead of 9,800. And then we can put in depth multiplied by width dx. And that guy is the 9,800 magic number I was talking about. And the depth here is x, and the width here is 7/8 x. So we're looking at 9,800, the integral from 0 to 8 of 7/8 x squared. And you're going to do dot, dot, dot. Isn't that just an ugly power rule? And according to the answer I have in front of me, there's almost 1.5 million newtons on that triangular plate. So the hydrostatic force acting on this plate is that. Let's take that same plate and have it submerged a little bit deeper. Now, if I choose to make the x value the distance from the top of the shape to here, if I choose to make that the x value, won't this end up being 7/8 x again, right? They'll have the same similar triangles. The only thing that would change here would be the depth. And wouldn't the depth now be, oh, and I have to tell you this number here. Let's suppose I do it 3 meters under the ground. Won't the depth be x plus 3, but won't A be 0 and B be 8? Do you see that you can adapt the question by keeping your x distance the same and just altering what depth is happening to? Do you see the only change to this question would have been the start and would be the depth part of the formula. The start and finish are the same numbers. This triangle and that triangle are the same. That means the width is the same. So when you looked at your formula, the main difference would be that guy there would now be x add 3. And if you moved it to 30 feet down, wouldn't the only difference be that would be x plus 30 now? So once you've set up something and you count the top of the shape down to the x, do you see how that makes it much easier to take that same plate and just sink it lower and lower and lower under the sea? And all you need to do is change your integral in one location, change the depth expression, right? Just change that one, right? If you count the distance from the top to the bottom as being x, it does work, but the math will look different and they tend to look uglier. And each time you move the thing lower, the numbers change significantly, that you have to play about with different solving of this as well to make it work. So my own preference, even if it isn't WebAssign's preference, is to choose the top of the shape to the strip, or as you're going to see in the next minute when we do the other way, from the bottom of the shape up to be the x distance. That tends to make the math cleaner. So we have one last guy to do. And that one last guy, not surprisingly, is 17. And we have some more. And we have half a circle. And in this water, that distance here is 10 feet. So we're back to hero units. This distance under the surface is going to be 1 foot. And we're going to find the total hydrostatic pressure. So first thing I'm going to do is I'm going to put in my little arbitrary strip. And step one, I have to figure out what I'm going to use for X. What distance is X going to represent? Now, it could represent the top of that guy coming down, right? So you could put a little dotted line there. I could do from there to there being X. I could do the top of the surface to there being X, but I'm not going to do either of those two. I am actually going to make this distance from the bottom to there is X. And the only reason I'm choosing that orientation is that that's going to make the width formula doable. If you try any of the other two, you will be able to get a width formula, right? Which basically means what's the width of that strip, but it's going to be in a very messy format. I'm not saying this isn't going to be messy, but it's not going to be anywhere near as messy. So I've chosen my X. Now I need to know who A and B are going to be. Well, let's put in the depth while we're at it. That total distance from the top to the bottom, you can calculate it. You have to do a bit of work. If this diameter is 10, won't the distance from the bottom to the top be a radius, which is 5, plus one more? Are you happy about where that 6 feet is coming from? Now, the depth of that strip is always measured from the surface to the strip. Now, that distance there is X. That distance there is 6. What is the depth in terms of X? This is 6. This piece here is X. What is the depth?
6 plus X.
6
Almost.
minus X.
Yeah, you're almost there. 6 take away X. Are we good so far? Now, when you're looking at this shape, the bottom of the shape to the top of the shape, the bottom of the shape is a 0, right? And the top of the shape is a 5. A to B is the X value of the top of the shape and the bottom of the shape, right? In this case, 0 and 5. Now you might think, how on earth are we going to get this guy called W? Well, we're going to be really sneaky here. That distance is X. I'm only looking at this piece, and I'm going to use symmetry. If I can find the distance from here to here, right, would you agree I'll be able to get the whole width? So why don't I just call it half a width? Now, there is one other side to this triangle, and that's this distance here. But I actually know what that is as a number. What is that distance here?
5.
Because it's in red radius. Now, we did similar triangles with the triangle questions, but I am not going to do similar triangles with this one. What technique am I going to use on this one, do you think?
Pythagoras?
Yes. And Pythagoras says the x squared plus a half w squared is 5 squared. So x squared plus 1/4 w squared is 25. So 1/4 W squared is 25 take away X squared. So W squared is 100 take away 4X squared. And so W will be the positive square root, because this is a physical distance, of 4X squared, which is that guy. So I have the width. Its formula is the square root of 100 take away 4X squared, right? That's what W is. But I'm going to pull out a common factor of 4 and get 2 the square root of 25 minus X squared. And that's as good as I can get. Okay, we should have everything that we need then. The force is going to be an integral from 0 to 5. And the magic number is going to be 62.5 because it's in feet. They're going to have the depth. We're going to have the width. And it's going to be 0 to 5, 62.5. The depth is 6 take away X times this guy, the width. And I'll take that guy, which gets me 125. And I've got an integral from 0 to 5, 6 take away X, the square root of 25 take away X squared dx. Oh, I just had to look at their answer. That's good. They actually did count it the same way that I did. For some reason, they've decided to call that distance y, but I'm not arguing over letters. It's close enough. Right, how do you think you're going to solve this? Well, there's a way we would solve it if we were going to do it exactly, but we're not going to do it exactly. We're just going to do it by plugging into the TI-84, and the answer that's going to come out is approximately 9,518. Now, if you wanted to do this integral as an exact answer, what you'd have to do is split it into two distinctly different guys. Okay. How would I integrate this right-hand side?
U sub.
And wouldn't the U sub be 25 take away X squared? 5 minutes later, you get the answer. How do you think I'm going to do that one?
X sub.
Yeah. Or look up the tables at the back. Remember the tables of standard integrals, because you'll find that guy there. And that'll take you, well, if you do X subs, it'll take you 15 minutes. If you do the table, it'll take you probably 5 minutes, because you have to plug in numbers, and you'll get that one. And when you add them together, are you happy to just say it's that one? So what I suggest that you do is that when you get to this stage, because your question is going to be a little bit different than mine, that you do it in your calculator and you come up with your right answer. I think I might have time for this. Let's see if we can do it. Y equals, so it's going to be, I'll use 125. 6 minus x's. And a square root of 25 take away X squared. And the window should be from 0 to 5. Let's do a zoom 0 to fit. See if it's actually, oops, what did I hit wrong? What did I do wrong? Nothing obvious. So insert a times, that should cause Shouldn't cause any trouble. Oh, there's my mistake. My bracket was pointing the wrong way. Okay. Then I can do zoom 0. I like zoom 0 because you see how zoom 0 caught that I hadn't, done the bracket right. And then I can do that guy. Now, if it isn't 9,518, it's because I can't count and I probably did a mistake somewhere. $9,518. I did it right. Okay, that is us. Last name. Move on. Are we good with this? Do you feel that you know enough to do rectangles, triangles, and half a circle, hydrostatic forces? All they're going to do now is change the numbers on you.
Professor,
Yes.
I have a question on that problem. Why the integral goes from 0 to 5?
Okay. In my question here, there's a lot going on in this picture, so I'm just going to redraw the guy. I decided to call this distance here x. And on the integral from a to b, the a and the b represent the start value of x.
Right.
Right, so at the bottom it's 0. Right? Right at the bottom it's 0, right?
Yeah.
And the radius of this thing is 5. So that's why that's 5.
Yeah,
And
I
radius
got
is
it. Yeah.
right?
Yeah, true.
So when you're thinking of what is A and B are dependent on what the start and finish value of the shape would be in terms of x. Any other questions? Apart from that, it's bye-bye, guys.